The earliest airplanes were handcrafted, experimental machines, light, fragile, and ingeniously simple, built from what craftsmen already knew how to shape: wood, fabric, and wire. Wood, spruce ash, provided a lightweight skeleton, and fabric covering gave the aerodynamic skin, a combo that was cheap, repairable, and perfectly suited to low-speed flyers. To make thin wings and light fuselages stiff, early designers used wire bracing and truss patterns that carried loads in tension and kept structures from collapsing. At the slow speeds of pioneer aircraft, aerodynamic forces were small enough that lightweight wood and fabric designs worked. But that advantage vanished as speeds and loads increased. Early designers faced a constant trade-off: add strength, and the airplane gets too heavy; cut weight, and it might not survive a gust. Design was a balancing act of materials and geometry. Wood and fabric need constant care: retensioning, doping, patching, and weather protection. So early aviation crews spent as much time maintaining structures as flying them. Let us look a bit more as to why wood and fabric were used in the early aircraft structures. Wood and fabric were very light, which was critical for early aircraft with low engine power. Availability and cost. Wood and fabric were widely available and inexpensive compared to metals at the time. Early builders could shape, cut, and join wood using simple tools without advanced machinery. Properly selected woods, like spruce, offered sufficient strength for low-speed flight. Damaged wooden structures and fabric coverings could be repaired quickly in the field. Early aircraft flew at low speeds, so wood and fabric could safely handle the aerodynamic loads. Early aluminum alloys and metal forming techniques were not yet well developed or reliable. Wood naturally absorbed vibration and shock, reducing structural stress. Let us now look at a case study of aircraft that were made of wood and fabric. The Wright Flyer was the world's first successful powered, controlled, and sustained heavier-than-air aircraft. Designed and built by Wilbur and Orville Wright, it represents the earliest practical application of wood and fabric aircraft structures. This aircraft is a benchmark example of early aviation engineering, where structural efficiency was achieved using simple materials and truss-based design principles. The primary objectives of the Wright Flyer were to achieve fully controlled flight in all three axes: pitch, roll, and yaw, while maintaining minimum structural weight. At the same time, the aircraft needed to possess sufficient strength to safely withstand aerodynamic forces and landing loads encountered during operation. Another key requirement was practical manufacturability, using limited industrial tools and resources available at the time. The Wright Flyer used spruce wood for the primary structural members, such as spars, ribs, and longerons, due to its high strength-to-weight ratio. The wing and control surfaces were covered with muslin fabric, tightened and stiffened using a chemical doping process. Steel wires were used extensively for bracing the wings and fuselage, forming a tension-based load-carrying system. Metal components were limited to fittings, engine parts, and fasteners to minimize weight. The aircraft featured a biplane configuration, which provided high lift at low speeds and allowed a shorter wingspan with improved stiffness. Each wing consisted of 2 wooden spars and multiple ribs, with fabric acting purely as an aerodynamic surface rather than a load-bearing skin. The fuselage structure was an open wooden framework with no stressed skin. Structural loads were primarily carried through wire-braced truss action, making the design lightweight but dependent on proper wire tensioning. Manufacturing was entirely manual and experimental in nature. Wooden members were shaped using hand tools and joined using mechanical fasteners and glue. Fabric covering was sewn and attached to ribs, then doped to shrink and smooth the surface. Wire bracing was installed and adjusted carefully to maintain structural rigidity. This low-technology construction approach allowed rapid modification and repair during testing. One of the most significant innovations of the Wright Flyer was wing warping, used for roll control. By twisting the wing structure using cables, differential lift was generated between the wings. Structurally, this required the wing to be flexible, yet strong, highlighting the advantage of wood and fabric construction, which allowed controlled elastic deformation without structural failure. The operational performance of the Wright Flyer was modest, but historically significant. The aircraft first achieved powered controlled flight on December 17, 1903, marking a milestone in aviation history. During its most successful attempt, it remained airborne for approximately 59 seconds, covering a short distance at a maximum speed of about 48 kilometers per hour. Designed to carry a single pilot, the aircraft's performance was limited in terms of speed, endurance, and payload. However, despite these constraints, the Wright Flyer successfully demonstrated sustained and controlled powered flight, thereby validating the effectiveness of its wood and fabric structural design and confirming the feasibility of heavier-than-air aircraft. Although the initial aircraft designs were constructed primarily from wood and fabric, their structural limitations quickly drove the need to investigate alternative materials. As speeds, sizes, and mission demands grew, the old wood and wire solutions simply couldn't keep up. Evolution was mandatory, not optional. Wood and fabric are vulnerable to moisture, rot, and UV. A plane that flies well today can be weakened by weather tomorrow if it isn't looked after. Early designers didn't fully grasp how repeated cycles slowly grow tiny cracks into big problems. Fatigue was a hidden enemy that only showed up after thousands of flights. Braced, lightweight structures worked at low loads, but had reliability limits. Rigging changes, hidden damage, and inconsistent repairs meant unpredictable in-service strength. What works at barnstorming speeds breaks down at higher speeds and larger sizes. Loads and aeroelastic effects rise non-linearly as aircraft scale up. Pressurization turns the fuselage into a cyclic pressure vessel. Wood frames, fabric skins, and wire bracing couldn't reliably resist repeated pressurization cycles required by high-altitude flight. That led to metallic aircraft structures.